All right, hello everyone. Welcome to my channel. This channel is for educational purposes, and we look at a lot of different, we try to go pretty deep on various theories of everything, cosmologies, all-encompassing theories, magnum opuses of dedicated crackpots, and other things that you might find esoteric and obscure. And today is the 330th video that we have done on Dewey B. Larson's reciprocal system of theory. And the reciprocal system of theory was originally proposed by Mr. Larson, articulated first in his two fundamental postulates that he came out with in the late 1950s. And from those two postulates, he eventually derived a theoretical universe and wrote a number of books based on that universe, on chemistry and physics and astronomy and economics, and then also a lot of metaphysical topics and philosophy, religion, psychology, biology. He's written on all those different subjects, and some of his followers have gone even further. But he is deceased now. He died in 1990 and left behind a very small group of followers, some of whom have written further, but this theory is just, we'll say, endangered. It's an endangered species of theory. And hopefully we're going to try to get it to reproduce a little bit through these videos. And today we're going to look at a paper that he wrote that is called The Search for the Ultimate. Now, first, let's just recap the reciprocal system real quick. In his first postulate, basically is the most important, and he says that we live not in a universe of matter, like the ancient Greeks would have said, not in a universe of energy, like the Einsteinians might have said, but in a universe composed entirely of motion. And there have been other people who came before Larson who did say that, including René Descartes and Thomas Hobbes. But what distinguishes Larson is that he defined the way he defined motion, which was he defined it as the relationship between space and time. This sets up a reciprocal relationship between space and time. Space and time are basically the same thing. They do not exist in and of themselves. They only exist together in motion. And they have the same qualities, three in particular. One is that they come only in discrete units. They're quantized. There is a minimum unit of space and a minimum unit of time. If you don't have a full unit, then you don't have that entity. And so that really means that the universe is composed of discrete units of motion. So he's kind of identifying, specifying more clearly what this is. The universe is composed of discrete units of motion. And then one other thing I'd say about the discrete units is that if you have exactly 1 unit of space in 1 unit of time, you have the speed of light, which is what Larson calls unit speed. Okay, so in Larson's system, the speed of light is really like the fundamental reference point, or the background, the state of rest, the origin, the ether. The speed of light is the midpoint of the universe, or the null point. In a universe of motion, this makes sense. Most of the legacy physicists are making their measurements from zero. You know, if they're looking at the speed of something, they're going to measure it from zero speed. You know, is it how much more is it than zero speed, or is it if it's going in a negative direction, yeah, then is it going, say, if it's a gravitational motion and the particles are going closer together, then that would be kind of like a negative motion, positive or negative from zero speed. But for Larson, he's measuring the motion from the speed of light. Is it plus or minus the speed of light? And so in Larson's universe, half of the universe is moving faster than the speed of light. That he refers to as the cosmic sector. And then there's half of the universe that's moving slower than the speed of light, which he refers to as the material sector. The material sector is really the only sector that the legacy scientists know anything about. And, you know, Einstein has his dictum that says that nothing moves faster than the speed of light. So that is showing that he is not taking into account half of Larson's universe. Now, another aspect of space and time and motion in his first fundamental postulate, Larson's, is that space and time, that they have what he calls a clock aspect, clock space and clock time. We're pretty much familiar with the idea of clock time. The clock is always getting later and later and later and later. But really, the clock is not getting later in any specific direction. It's just getting later. You don't say that the clock is getting later in this direction, but you just say it's always getting later and later and later in basically a uniform flow, the flow of time. And we're used to that concept. But then he also says that, you know, any quality that adheres to one adheres to the other. So there's also what he calls clock space. And clock space is that everything is moving farther and farther and farther apart. And the visual that you would use for this is a balloon with dots on it. You take the balloon with dots on it, you blow up the balloon, all of the dots are moving away from each other. Again, but in no specific direction. So they're moving away from each other, but each one is moving away from each other one. And you're not able to like actually determine the motion of one until you specify which one you're measuring from, which one is your reference point. So what Larson calls that a scalar motion. A scalar motion is a motion that has a magnitude only. It does not have a direction, or does not have a specific direction. The direction is only specified once you identify a reference point. And so this model of the clock or the expanding balloon is showing you clock time and clock space. So to add to this, the universe is made entirely of discrete units of motion. You can now say that the universe is made up entirely of discrete units of scalar motion. And then the third prong of the first postulate is that space and time both have their coordinate aspects. Now, again, this is something that we recognize in terms of space. We recognize coordinate space, x, y, z coordinates, 3 dimensions of space, or possibly 4. If you want to look at the model of the cube, if you're measuring from the faces of the cube, you have three dimensions. But you can also use tetrahedral coordinates with the cube, and where you're using the diagonals of each face, then you would have 4 dimensions for a total of 7. But either way, space has its coordinate aspect, but time also has its coordinate aspect. So there are 3 dimensions of time as well. Now, this is something that we're not familiar with. And basically, the reason we're not familiar with it is because it occurs in the cosmic sector, in the sector that's moving faster than the speed of light. When you cross that speed of light boundary, which the legacy scientists don't admit exists, the cosmic sector is basically a mirror image of the material sector. It is identical to the material sector, except that it is the reciprocal of it. And that what you have to do is you have to invert the roles of space and time. So if you're in the material sector, where we are generally located and where we perform our measurements and our observations, we see 3 dimensions of space, and we see clock time. We observe clock time. The clock is always getting later and later and later, and we're in 3 dimensions of space. But if we cross over to the cosmic sector, then we have to invert, and we have 3 dimensions of time, and we have clock space. Space is always getting farther and farther and farther apart. So that's kind of how it works. So basically, the universe is made entirely out of discrete units of scalar motion that have 3 dimensions. 3 dimensions of discrete units of scalar motion. And then the second postulate is more or less that the universe conforms to the relationships of ordinary commutative mathematics. Its primary magnitudes are absolute, and its geometry is Euclidean. Okay, so that part about the Euclidean geometry has been disagreed with by some of Larson's followers, and it's been replaced by projective geometry, which is a more expansive view of the geometry that also includes Euclidean geometry. So it was that is a modification that some of Larson's followers have tried to insert in revising the reciprocal system of theory. Okay, now we're going to try to flesh this out a little bit more in Larson's article here called The Search for the Ultimate. From the very beginning of the kind of disciplined thinking about the physical world that we now call science, one of the major objectives has been to identify the basic constituent or constituents to answer the question, what is the world made of? The earliest theories of which we have detailed knowledge, those developed by the Ionians, Greeks, in the years from about 600 to about 400 BC, and by the Chinese around the same time, were of two general types. One group of philosophers, reasoning from an assumption as to the unity of nature, argued for a single constituent. Water was the usual choice, although there was some support for air. Another group contended that the great multiplicity of physical forms required the existence of a number of basic constituents. The most popular choice among the early investigators in the West was a four-element universe constructed of earth, water, air, and fire, an identification that achieved a kind of an official status when it was accepted by Aristotle. The Chinese recognized five basic elements, omitting air and adding metal and wood. One problem that persisted throughout this development of thought was the question as to the cause or causes of physical change. The investigators who laid the foundations of science concentrated on explaining existence rather than change, that which is rather than that which happens. One influential philosopher, Parmenides, even went so far as to deny the reality of change. By including fire as one of the basic elements, the later theorists provided explanations for many of the observed physical phenomena, and Aristotle filled in the gaps with some inventions, including a prime mover to account for the motions of celestial bodies, and a theory whereby every physical object tends to move toward its natural place. With the benefit of these additions, the four-element hypothesis was able to hold its ground for nearly 2,000 years. But the gradual accumulation of observational knowledge eventually forced a change in thinking, and the scientific revolution that began almost 1500 AD about 1500 AD, replaced the ancient Greek concepts with some very different ideas. Modern science has arrived at a consensus which accepts the concept of a universe in which there is only one type of existence. But this is not a one-component universe, as the distinction between what is and what happens is retained, and this requires additional components to explain change. This currently accepted theory envisions a universe of matter, one in which elementary particles of matter exist in a framework provided by space and time. Physical activity is explained by the existence of certain fundamental forces, each of which produce a force field that acts upon matter. One of the primary objectives of present-day science, basic science, is to devise a unified field theory that will unite these various force fields. This is the task on which Einstein spent the last 20 years of his life. It remains as elusive today as it was to him. Strangely enough, no one seems to have considered the question as to whether forces can be fundamental, that is, unexplainable in terms of other entities or phenomena. Once this question is asked, it obviously has to be answered with a decisive no, inasmuch as the force is defined scientifically as a property of motion. Motion is measured on an individual mass unit basis as speed or velocity, and on a collective basis as the product of mass and velocity. This product represents the total quantity of motion of an aggregate of matter, and in earlier days it was specifically designated as the quantity of motion. More recently, the term momentum has been substituted, and this has had the unfortunate result of obscuring the real nature of the quantity. The time rate of change of the motion of each individual unit is acceleration, while the time rate of change of the total quantity of motion is called the product of the mass and the acceleration, which is called force. Thus, force is actually the total quantity of acceleration. In the cylinder of a steam engine, for instance, the total quantity of acceleration, the force, of the moving steam molecules that is exerted on the piston can be calculated by statistical methods that evaluate the rate of change of the total quantity of motion, the momentum, of the steam particles. This total quantity of acceleration can then be divided by the mass of the piston to arrive at the acceleration that is imparted to each of the mass units of the piston, and thus to the piston as a whole. From the foregoing, it follows that there cannot be any such thing as a fundamental force. Every force is necessarily, by definition, a property of an underlying motion, the rate of change of that motion. Clearly, those who are seeking a unified field theory that will unite the so-called fundamental forces are aiming at the wrong objective. Instead of looking for a unified theory of the forces of nature, they should be looking for a unified theory of the motions of nature. It is the motions that are fundamental, not the forces. Meanwhile, it has also become evident that matter cannot be the basic physical constituent. We now know that there are processes whereby matter can be converted to non-matter, and vice versa. For instance, matter can be converted to radiation. And since matter is not a form of radiation, and radiation is not a form of matter, it follows that both radiation and matter must be forms of some underlying entity. This has been recognized by many of those scientists who have considered the issue, and attempts have been made to identify the common denominator that obviously must exist. Heisenberg, for instance, suggested that energy might be the basic quantity, although he admitted that he could not see how energy could meet the requirements. Many other investigators have favored motion as the fundamental entity. Thus, whether we approach the question from the standpoint of the nature of substance, that which is, or from the standpoint of the nature of change, that which happens, we come down to motion as the most likely candidate for the position of the fundamental constituent of the physical universe. Even before all of the evidence now pointing in this direction was available, the potential ability of motion to unite that which is and that which happens was clearly recognized, and a long list of scientists and philosophers, including such prominent figures as Descartes, Eddington, and Hobbes, tried to construct theories based on the concept of a universe of motion. None was successful. Indeed, none of them really got off to a good start. But the complete failure of the present-day concept of a universe of matter to meet the tests of validity makes it imperative to continue the efforts along this line, and calls for a more critical examination of the obstacles that have hitherto prevented taking advantage of the potential that is inherent in the concept of a universe of motion. Okay, we're going to stop it off right there and resume the second part of this paper tomorrow. I think we should be able to get this done tomorrow. You know, if everything goes well. And yeah, so I think we did about half of it here today. And thank you for tuning in today. And tune in tomorrow to hear the second half. And have a great day.